Thank you, guys. Can you hear me? Yeah. All right. Right. So this talk is not going to be very technical. So you can all relax a bit after the pizza, I guess. I wanted to talk about medical validation of non-interpretable models because that actually determines a lot of the stuff that we do here at Babylon. And in case you don't know, so Babylon, I sort of need to give you this sort of motivation slide at the start to a startup. So Babylon has a quite simple mission, which is to put an accessible and affordable health service into the hands of every customer. So basically we want to make healthcare much more accessible and much more affordable, right? And the main product is an app that you see there that you can download, by the way. And through that app, you can have consultations with a doctor, basically. So, in order to achieve this mission, we need to basically automate primary care, right? So we need to become really good at identifying people that do not need to see a doctor and people that really do need to see a doctor. So when you come to the app, you come with a presenting complaint, you speak maybe with a chatbot or something similar, which identifies if you should really see a doctor right now or if you shouldn't. And that is obviously quite sensitive, right? So we need to really make sure that the models that we use and the methods that we employ are actually safe. Right. So to get an idea of the problem, it sort of makes sense to look at the problem from like a machine's point of view, at actually what a doctor does in like real life, right? And so much of the stuff is super obvious, right? But to a machine, these are actually quite difficult problems. So first of all, you go to a doctor, you have a conversation with the doctor so he can understand you, he can speak your language, right? The doctor has a conversation with you, the doctor can actually see you, right? So when you have a rash or something, the doctor can look at your rash and diagnose you. And beyond these sort of main perceptual skills, they also know stuff about medicine. And finally, they can diagnose you. So even though diagnostic is a really big issue for us, so we spend a lot of time developing a diagnostic system, the other challenges still remain. And if you think about it, if you look at like related work and stuff, these perceptual challenges are all right in the middle of deep learning, right? So there are some alternative models, but basically everything there is outperformed by some sort of deep learning approach. So we don't really have a choice, but to achieve the mission, we do need to employ some deep learning in the company. And that leads to the usual problems. Like, many people are concerned about this because we're basically training a black box, right? So if we train a deep learning system, we can't really look into it. We don't really know what's going on. So can we really trust a non-interpretable model to do the right thing every time? And the answer to that is obviously not. Right? So there's no way that we can definitely know for sure each time that the model does the right thing. So there are many application areas, like if you think of computer vision or NLP or something, the input space is basically infinite, practically speaking. So you can't really do regression testing or anything, so you can't even enumerate all the cases that you could test. So you really need to take a guess at how good your model is. So in the same sort of tone when people talk about the non-interpretability, they also mention that we should always use interpretable models. And then the question is, so can we actually trust an interpretable model to always do the right thing? Right? And the answer to that is also, we can't. Just because the model is interpretable doesn't mean that we sort of magically solve this problem of always predicting the right thing. We can always just make like an empirical argument about if the model works or not. So we can look at the performance of what we see and compare that to what we expect. And we can take a look at if that is sort of in alignment with what we want to deliver to our customer. Right? So we basically need to demonstrate that it works well enough to convince doctors that it's safe to deploy. But the reality is, if you use an interpretable model or non-interpretable model, both of them will occasionally fail. So there's no way you can avoid that your model will fail at some point. The only difference is that the interpretable model gives you a bit more insight into what went wrong afterwards. But it doesn't prevent you from failing. So it's not just that you take like a decision tree and suddenly everything works. Right. So what is it that actually makes a model safe to use in medicine? And this is very high level, right? So if I have some sort of user input, so let's say, I don't know, I have an image of a rash or whatever, and I correctly classify that image as a rash, then if that is an accurate prediction, that is obviously safe, right? Because our doctor annotated it, so we compare it, it's fine, right? But also inaccurate outcomes may still be safe. So if you think about autonomous cars from earlier, let's say you have like your image segmentation model that mistakes a parking car with a house, right? Not much damage there, it's still fine, right? So there are cases where stuff is being confused and the model basically makes a mistake, but it's still, practically speaking, safe. So the safety doesn't really depend only on the model, but it also depends on the content that sits behind the model. And usually in the type of stuff you predict, there's often a lot of overlap. So particularly with images, but also with text, there's often ambiguity and so forth. So you need to really take a look at the whole system instead of just the model to assess if it's safe or not. And also safety is not the same as accuracy. And usually if you do it right, then safety is usually much larger than accuracy. Right? Since there are many more cases where a confusion might be, let me rephrase that. So the accurate ones are definitely safe, and some confusions are safe. So overall the safety is higher than the accuracy. Right, and this really drives like the whole sort of design paradigm of like the interaction at Babylon, which is this sort of designing for failure. So we need to, since we know that we can't really trust the model to do the right thing all the time, we need to make sure that if it fails, that failure is not really catastrophic, but that we can deal with it in like a safe way. And I have one example for you for that. So some of you might have seen this before. Anyway, so if you want to build a very simple chatbot, like a natural language interface, think like Siri or something, you usually do that in like 2 steps. So you have some sort of user input, then you have a first level of processing, which is like a very high precision system. So basically, maybe a bunch of rules, like regular expressions, things like that. If they match, then you have a very high confidence that you're doing the right thing. Right? But it will only match on a small subset of inputs, so the recall is pretty low. But you still have to deal with all these inputs that are rejected at the first phase. So you need another phase, where by definition you can't really use rules because you already use the rules up here, right? Where you need to have something that has very high recall. And if you think of Siri, if you like tell it to set your alarm for tomorrow 9 a.m., it will do an amazing job, which is sort of this first step, right, where it has a very high precision in what it should do. But if you ask something where it doesn't have like a pre-made routine for it, it will just send you to Google, which in this case will be this high recall service. So if you have, so let's say the correct thing happens. So the user says something like, I don't know, I have a headache, right? And the bot predicts, right, I should ask this person about headache. So I should enter the headache flow and ask some questions. Then in this case, it's fine. Everything's fine, it's safe. Right? But what happens for this reject case? So in a simpler chatbot, so if you build like a customer service chatbot maybe, the chatbot would just say, I don't know, can you rephrase your questions? Or I can deal with this, or something like that. Which can be quite a snappy interaction because you can make it very nice for these sort of social interactions. But what we actually say is something much more cumbersome on first sight, which is like this big text block there. So what does it actually say there? Which is that so first it says that the response indicates that it's like it doesn't know how to deal with it. So it says like, sorry, I would like to be able to help. I might be able to assist if you rephrase your questions. Secondly, though, it will point the user into the place that might provide help that they didn't get with the chatbot. So it would say, alternatively, our clinicians are always happy to help. We'll do everything they can during an appointment, and so forth. And lastly, there's this safety net that it says that if you think there might be something seriously wrong or your symptoms are changing rapidly, please go to the nearest emergency department. Right? So, and even though this is like a trivial thing to do, right, to have a response like that, what happens then is that all the responses that will be rejected by your model automatically become safe. Because this is always a safe response. I can always, for any input question, if I would only have a chatbot that always says this, it would be 100% safe. Right? It would also be useless, but it would be safe. So knowing this, knowing what will happen with our output in this way of the model, we can actually use this knowledge to inform the process of how we create the model as well. So This is supposed to be a confusion matrix. I'm sure most of you have seen a confusion matrix before, where the rows contain examples annotated to belong to a certain class, so let's say class I, and the columns contain the examples predicted to belong to class J, and if you have a column ij, those are the ones that are annotated as class I but predicted as class J. So far so good. We always know that the ones that are on the diagonal, are definitely safe because we're doing the right thing. But knowing that our reject response is also safe, we also know that all of these responses are safe, where some objective class was confused with the background. And we can actually use that, right? So we can, for example, we can change our loss function to penalize stuff that is off the diagonal, right, but not with the background. Or we can, which is a bit easier, which is to just change the composition of your mini batch to like over-represent this class. Then we'll also be much more likely to confuse stuff with the background than with a non-objective class. And lastly, we sort of get this for free nearly if we do a rejection based on some sort of degree of confidence. And this might be just the probability predicted by the softmax, or it might be something more involved, like if you use dropout or anything. And that will usually lead to this behavior that the off-diagonal entries, if you have an over-represented background, will be very sparse, while the model will largely confuse with your background class. Right, so we can actually, knowing this, we can build this safety into more than just one class. So you can think of having another class that is safe, where the response is automatically safe. Or you could have, if you know that, for example, the example earlier of the parking car at the house in like an image segmentation task will be some cell somewhere on the off diagonal, and you could say that's safe as well. And using this procedure, you can maximize your safety while also maximizing your accuracy. Right. So let's say we have this. How do we go from this to having a model that we're actually confident is safe enough to deploy? And for that, we developed like this Babylon, specifically this continuous validation and surveillance procedure that we use that we subject all the models to that we develop. And that's also the reason why we have a lot of doctors within the AI team that will help us do these tasks and annotate a lot of data for us. Right, and it's actually very simple. So, right, the problem is the bootstrap. So when you want to start all this whole process up, you need to find some way to define like some initial corpus, right? So you scrape the web, don't know. You show that to a bunch of doctors to annotate it, and then you use that to train like sort of your first model. And using that train model, you gather more data, and you use that model to infer whatever the model wants to infer on that data, and you show that back to the doctor, which goes through it case by case and tells you if it's safe, if it's accurate, and so forth, and what the actual class should be. And that way you kind of have a loop, right? So you start off small, you do the validation, you find out it doesn't work well, you go on, until you actually reach a threshold where your safety is along the lines of the expectations of the doctor, from which you can actually then deploy it. And once you have a deployed model, you can, on one hand, get unlabeled data from like just usage, right? But you can also, or you have to actually, also do this post-market surveillance. That is that a doctor will look at a representative subset of like the first queries that go through the model to see if the model is still safe even after it is deployed. And this process is actually compliant with regulations for medical devices in the UK. So the app is a medical device class 1, and as part of that process we have to submit documentation like this, and they're actually fine with this. And it could be potentially extended to also involve a class 2 device maybe, but we will still think about that. Right. So, but what happens when you train a model and the doctor actually finds out that something is wrong, right? So how do you know how to fix the problem that you discovered in the predictions of the model? So as the model is non-interpretable, it's not that straightforward to say, oh, this feature is wrong or whatever. You actually have to dig quite deep down into the predictions of what it actually does. So then there are two main things that you can do, right? So you can re-annotate data or add data, right? Or you can redesign the outside of the system that will affect the safety, right? To better cater toward the performance of the model. But that leads to two problems. So how do you find the areas of the input that is actually problematic? And like, how do you know how you should change the outside system in order to become more safe? Right. Let me give you a quick example if I can. Right. The approach we found that works really great are embeddings. Right. So virtually all deep learning models at some stage in their pipeline will have a layer where you can extract good embeddings. And usually that's right before classification occurs. So right before what feeds into your softmax, that is usually a good representation of the input data. And what you see here is a t-SNE, which is a dimensionality reduction method, down to 2 dimensions of like the hidden state of an RNN that read a bunch of input data. And every dot, can I actually, yeah. So every dot in here represents an input sentence. And I must say that this is data from internal testing, so I'm not giving away any user data. And each dot is colored according to a class that was annotated by a doctor. In this case, these are a bunch of medical categories like abdomen, chest, back, non-anatomical, head, describing like general medical problems. And overall you see it's pretty well clustered, right, which is good. But it's also not a surprise because this was trained to predict those classes, right, so they will be well separated. But where it's interesting is this block here in the middle, for example, where you see a lot of red points, which are sexual health, a lot of abdomen points, which are the blue ones, and cases that relate to your bottom, basically. That's okay, right? You always have the best examples at medical companies. And you see that there's a lot of confusion, right? So these are very close together, right? So one simple thing, if a doctor says, all right, the separation between these classes isn't very good, you can look at the embedding and you can actually identify, right, I should actually have a separate class for, like, I don't know, genitalia related questions that would capture all of these, right? So if you go through your data again, you annotate it again, you learn a model to predict that class, that confusion will go away. So you automatically increase the safety of your system because you removed all that confusion. And for the first case where you want to identify which area might be problematic, you look at where in this embedding space your problematic input query would go, and you look at the ones that are closest to each. And you have a doctor re-annotate or check the quality of those annotations, because also doctors do make mistakes, obviously. And that's like a quite scalable approach to this problem. And we found it to work really well, actually. Right. So this is already summary. So just a few concluding points, which is so interpretability doesn't really matter for the safety of the system. If the model is interpretable or not, at this stage it doesn't matter. Interpretability just affects your recovery process. So once you know that something went wrong, how do you fix it? You obviously want to you want to have to maximize the safety, and there are different ways to maximize the safety, either through the model or through the surroundings of the model. Safety is not the same as accuracy, and obviously this needs to be subjected to quite careful validation process. Right. Since this is a TensorFlow meetup, I want to point you quickly to our Babylon Health repo on GitHub, actually called Babylon Partners. There are 2 repositories here. This is a repository for a project that we published on ICLR this year, which surrounds the alignment of word vector spaces. So in case you're interested, this is actually containing alignment matrices for 78 different languages with which you can build multilingual classifiers, which is pretty cool. And the other one on the right, TF Bridge, is an open API specification, so basically a REST wrapper around TensorFlow serving that saves you from all the hassle with protobuf, in case you ever tried that. Right. Lastly, recruiters told me I should say this: we're hiring, right? So we're always looking for machine learning scientists and engineers. We're looking for NLP scientists, NLP engineers, and we're also looking for people that are very good with Bayesian stats for scientists and engineering position as well. All right, that's it. Thanks.
If you go back to the slide where you had the embedding in order to, this one.
Do you mean
so like these 3 classes that are really close, then you solve the problem by just making another class that lumps them together. That's easier to resolve.
So this is an old version of the chatbot. The newer chatbot is much better at separating these classes, so we still have them.
Yeah, exactly. So for security, you kind of lump them up in one class for the beginning, just to remove the confusion, then what do you do to be able to separate it better? You add training examples for
Yes, so there will be, so you add training examples on the boundaries, then you sort of force it apart, but there are also limitations to that. It might just be that the in your word representation, those sentences are just too similar. And if you actually compare the performance of humans in annotating those tags, it's also not very great. I think the solution that actually came out of this, on one hand we improved the model, so it's better at predicting this stuff, but also that the content where this points to are basically like question flows about like certain medical topics. They were expanded to include the other topics as well. So in the end, it doesn't really matter which one you go down. If you have like a critical symptom, it will be caught in either of the flows, which is another approach, basically. Yeah.
There's a big aspect about privacy when it
Yes.
comes to medical data.
Mm-hmm.
How you deal with the private information we share, especially you do learning.
Mm-hmm.
And
Yes.
as a user, maybe I don't like to share or learn from my data.
Yeah, so to give you an idea what data we use right now. We do around, I don't know, maybe 1,000 or more consultations per week, which are video recorded, but that is not data that we have access to for exactly that reason, because at the moment, for example, we can't, so we would be very interested in the transcripts of those recordings, but we can't just simply use Google services or whatever to send the data to get a transcription. So we are very aware of this, the privacy issues surrounding this. So what we actually built to preserve the privacy in these cases is like anonymization tools that strip the personally identifiable data out of text data. So remove names, we use addresses, remove telephone numbers, remove everything that could be personally identifiable, and replaces it with sort of bogus names to keep the sort of structure semantically the same.
Did you try a solution for having public data, then you have a learned model, and you can actually personalize it or fit this model to specific user?
So it's a problem we haven't yet come across, this sort of personalization aspect. And it leads to all sorts of problems with this approach of validation, by the way. It's certainly very interesting to have like if you think of like a personal model that runs on your phone or something, right, which is certainly possible. But on one hand, there are problems with the validation if you have a model that adapts over time, because it becomes much more difficult to be confident that the model does the right thing, because if it depends on too much context, if you understand what I mean. So that's one issue. On the other hand, we have a duty of safeguarding and things like that, since we're a medical company. So think about a person repeatedly asking about bruises why do children bruise easily or something. We need to know that they continuously ask about the health of a child in order to fulfill our safeguarding requirements. So we couldn't really let you run it all in private on your phone for that reason. Which also sort of depends on the market. So that's in the UK definitely. But yeah.
So since we're talking about privacy, next year we have GDPR, and basically there's going to be a duty to release data upon request from each user. In that case, what does really data mean? Is it just the initial data and so on, or everything that's associated with that, including what you've learned about it?
I'm not actually 100% sure, to be honest. So I think this regulation is mostly about the medical records, which affects your sort of longitudinal records. If we are able to strip personal identifiable data from your data.
GDPR, it's about any data that is going to be stored.
Well, the only solution is that we need to strip it from our training set. That's really, which is something that we can do. I mean, there are already, like, for example, if you use like the UK Biobank or something, maybe some of you are familiar, they often release like change requests as people have retracted their data, which we remove then from the data set.
Another question. So one of the requirements of GDPR is that I will have to be, as a user, I will have to be able to take out my data in an automated way from whatever service.
Oh, okay. Yeah, we can do that. So we can offer an interface for that. Sorry.
Will that be just the conversations that I'm going to be able to take out, or everything that you've learned about?
So that should really be everything, right? So that involves all the interactions that you have with the chatbot, which is text, but also the appointments that you had, the data that was collected about the appointments, prescriptions that you had, support questions that you had. That will all be. We're actually working on like a. So it's not centralized storage system, but we have like one central representation for the user that we can query securely for medical info, and that will just basically just be an endpoint for that service. So we can definitely do it. The removal part, I think that is harder from like these machine learning models, because it will basically mean with every request we might need to change the model. But there's actually, Dan will talk about some models that are much more resilient to that. Where we can actually simply pull out content without affecting the overall model. Yeah.
Thanks. So I see you're interested in Bayesian people, so maybe you're thinking about things like this already. But you touched on it a bit with uncertainty measures and getting away from a deep learning point estimate.
Mm-hmm.
If your model can hold its hand up and say, I'm not certain about this example, I need a pair of human eyeballs, that's great. But I guess the cases that are bad for you guys in this domain are things that you get wrong, but you're very confident about, very certain about.
Yeah.
Have you thought about that, or how do you mitigate or account?
So we are working on using Yaron Gal's work on this, as I guess everybody else does. Like you already. So there are definitely cases where the model is wrong and has a high confidence. And there are, like the sort of standard approach, I'm not sure if everybody knows, is that you basically just keep dropout on, and you sample a bunch of points, and then you basically estimate the variance in that, and that variance is related to the confidence that the model has. That is something that works surprisingly well, yes. And we are looking to incorporate that into a production system. It also comes at a speed penalty though, so that's something to consider. If you have to do 100 times the work, that can have an effect on your production system.
I guess in this domain it's sort of...
It is definitely worth it. I mean, we do try, did I? Yeah. So you're referring to the rejection based on the confidence, right? So if you train this in the right way. It is very it happens very, very rarely that an off-diagonal element will have high confidence. But it's not a general solution, that is true. Yes?
My question is maybe not so specific to this, but potential other line of activity connected to this, obviously. It seems because of the limitations you have, it would be quite hard for you guys to use, for example, reinforcement learning, because it would almost crash with this type of limitations.
Yes.
Do you think there is a space within the limits of this for reinforcement learning?
I think, so closing the loop directly between production and training is something that I wouldn't be able to get past the doctor. So you all seen Tay and whatever from Microsoft, what happens if you do that, or could potentially happen if you do that. So the sort of the loop between production and training will always have, there will always be a doctor in the way. So we can integrate it immediately. I think there's a lot of space for reinforcement learning in medicine in general. It's just particularly hard because so if you run a game or Go or whatever, best examples, or in general games, you have a nice platform to simulate things. You know how to predict the future very well, right? Yet that doesn't really work in medicine because nobody has a generative model for patients that is good enough to be used in a reinforcement learning setting yet. Unless you have that, it's like it would take so much time and so many input examples that it would basically take forever for the reinforcement learning model to fit. If you can't have some sort of simulated source.
You don't have the ground truth.
Yes, that as well. But you could. I mean, if you take it one step further, then you could say, all right, the ground truth will come later, right? You know if the people get sick again or something. So if you let's say you would build a diagnostic systems, for which you, by the way, don't use deep learning at the moment. So that's where we're interested in the Bayesian stats people, because we're also building a big diagnostic piece. So, but you could combine that with some reinforcement learning approach that over time sees if the diagnosis was actually correct and the treatment that it proposed was actually correct. Does that make sense? But it's difficult.
About genetic models.
Generative models, yeah. I like generative models. It's as I said, the ultimate model will be a generative model for patients. If anybody could develop that, I mean, we are looking into that direction, but it's a difficult task because some of the data that you need is also not really accessible. So
It's a good problem for GANs because in GANs you don't need to have the exact truth. You just need to know if it's some set of data is reliable or not reliable.
yeah, maybe we can take this offline. Where else? Yes.
Hi, so I really appreciated your confusion matrix, how you kind of encourage the model to throw its hands up and give a safe response. But I noticed that that's kind of a tunable parameter, say how much you penalize the loss function.
Yeah.
And it's a balance between how safe is your product and how useful is your product, which means presumably someone here has to decide what's the right value for that, how safe do we want to be at the cost of having a less useful app. How did you make that decision?
So the doctors actually do not decide how accurate the model has to be. The doctors only decide how safe the model has to be. How accurate it will be will solely depend on us building the right model and finding ways to train it to maximize the performance. But they don't, they wouldn't let a model through that has low safety just because it has 5% more accuracy. So yeah, does it answer your question?
Yes. I mean, I guess the question is still then, at what point did you make that how safe is safe? Let's have a follow-up.
Yeah. So well, that is a clinical decision basically. So we usually go by 99.8 or 99.7. Do I have something here? Wait, I can. I thought I had it on a slide, but I don't have it anymore. So we, at the moment, the system that is deployed right now has a safety rating of around 99.8. And in a lot of those cases that we found during the validation, it's actually also mistakes by doctors that occur during the validation process as well. But I'm not sure if you ever work with a doctor. They're quite hard to convince. You're welcome. Right. Should we? Yeah. Sorry.
Last question.
Okay.
It's technical stuff, but if you know streams from Google DeepMind, the application, maybe it's slightly different, but I expect them to see also they can produce something similar to what you're doing here. And the question is, what in your plan to have to make your product actually, or what you produce better or have an advantage than what Google may produce?
So that's actually quite a deep question, if you will. So I don't think Google is in the business of becoming a medical company. I can tell you that it's a lot of pain to be an actual medical company that also supplies an actual health service, because it comes with a whole bulk of regulations. And I think Babylon is in a quite unique position in this sort of attempt to automate primary care. Most AI sort of companies that look into healthcare mostly look at secondary care for exactly that reason, right? Because you have a more well-defined problem, you have a more well-defined regulatory landscape. I think what sets us apart a bit is that we actually also provide the physical service that to support this. So we don't just have this AI piece that we're developing, but we also have a layer of sort of virtual consultations that you can have. So you can actually speak with a doctor, which makes a big difference.
They have also access for data from the images.
Yes, but you can't access any doctors through Google, and I'm not sure that will change anytime soon. Yeah. Right. Thank you.